The 8085 microprocessor speaks a simple language made of opcodes, operation codes, and operands, the data they act on. Think of an opcode like the verb in a sentence. It tells the processor what to do, such as add or move. The rest of the instruction, the operand, is the noun that tells the processor where to find the numbers or where to store the result. In the 8085, each instruction is 1 to 3 bytes long. The first byte is always the opcode. The high-order 4 bits, the left half of the byte, are called the opcode field and roughly decide the type of action, while the low-order 4 bits, the right half, often hold a register identifier like A, B, C, D, E, H, L, or M. For example, the instruction MOVBC has the binary pattern 01, 000, which can be read as 01 equals the MOV group, 000 equals destination register B, 001 equals source register C. When an instruction needs an extra address or immediate data, the next 1 or 2 bytes follow the opcode, just like a postal address that comes after the street name. This regular layout lets the 8085 decode any instruction in a few fast steps, much like a child quickly recognizing a familiar picture in a storybook. The 8085 instructions can be grouped into 5 everyday categories, just like tools in a toolbox. Data transfer tools that move things around. Examples: MOV copy a byte from one register to another, MVI load an immediate constant, LD a load from memory, ST a store to memory. Think of it as taking a toy from one shelf and placing it on another. Arithmetic tools that do math on numbers. Examples: a DD, a DI add immediate, SUB, SUIINR increment, DCR decrement. It is like counting apples in a basket and then adding or removing some. Logical tools that compare or combine bits, similar to turning lights on/off in specific patterns. Examples: a NA AND, XRA XOR, ORA OR, CMA complement. Imagine 2 transparent stickers with holes. Overlaying them shows where both have holes and, or at least one has a hole OR. Branch tools that decide where to go next, like a choose-your-own-adventure book. Examples: JMP unconditional jump, JC jump if carry, JNC jump if not carry, JZ jump if 0, JNZ jump if not 0. The processor follows a new page number based on a condition. Control tools that start, stop, or reset the story. Examples: NOP do nothing, HLT halt, RST restart, DI disable, EI enable interrupts. These are like pressing pause, reset, or turning a flashlight on/off. An addressing mode tells the 8085 how to find the data it needs, similar to how you might look for a book. You could pick it up from the shelf, ask a friend for the title, or read a note that tells you where it is hidden. The 8085 supports 5 main modes. Immediate: the data is placed right after the opcode. Example: MVIA 0x3E loads the constant 0x3E into register A. It's like writing the number directly on a sticky note attached to the instruction. Register direct: the data lives in a register. Example: MOVB, C copies the contents of C to B. Imagine you have a cup, register C, and you pour its water into another cup, register B. Direct memory addressing: a 16-bit address follows the opcode. Example: LD a 0x4000 reads the byte stored at memory location 0x4000. This is like having a street address written on the envelope. Register indirect: the pair H-L acts as a pointer to memory. Instructions like MOVA, M treat the address formed by H, high byte, and L, low byte, as the location to read from. Think of H-L as the hands of a clock pointing to a specific shelf. Implicit: the instruction itself knows the operand, no extra data needed. Example: CMA complement accumulator always works on the accumulator. It's like a self-closing door that always flips its own state. Practical scenario: to copy a block of data from RAM to RAM, a program often uses the register indirect mode with a loop that increments H-L, similar to a conveyor belt moving items one by one. The flag register, also called the status register, is a small set of lights that tell the processor what happened after the last operation. There are 5 important flags. Sign S set if the most significant bit of the result is 1, that is, the result is negative in 2's complement. Imagine a traffic sign that lights up red when the outcome is negative. 0Z set when the result is exactly 0, like a scale that beeps when nothing is on it. Auxiliary carry AC, used mainly for binary-coded decimal BCD adjustments. Think of a carry over when adding decimal digits, similar to moving the one to the next column. Parity P, set if the result contains an even number of 1 bits. Picture a teacher counting heads and raising a hand when the count is even. Carry CY, set when an addition generates a carry out of the most significant bit, or a subtraction needs a borrow. It's like a water bucket overflowing. These flags are consulted by branch instructions. For example, JZ address jumps only if the 0 flag is set, meaning the previous calculation gave 0. By chaining arithmetic and logical instructions with conditional jumps, a program can make decisions, repeat actions, or stop when a condition is met, just like a child playing a game that continues until they roll a 6 on a dice. Every 8085 instruction is executed in a number of T-states, machine cycles. One T-state is one tick of the internal clock, similar to a heartbeat. The clock period is usually 0.5 microseconds for a 2 MHz crystal, so each T-state lasts 0.5 microseconds. Simple instructions like NOP need 4 T-states, just 2 microseconds. More complex ones like LD address need 13 T-states, 6.5 microseconds, because the processor must read the 2-byte address and then fetch the data from memory. Understanding the timing helps you choose the fastest instruction that still does the job. For example, to increment a register, you can use INRB 5 T-states or DCRB 5 T-states. Both are equally fast, but if you need to add one to a memory location, you must use INRM 10 T-states, because the processor first has to calculate the address from H. When designing real-time systems, for example blinking an LED at a precise rate, you add up the T-states of each instruction in the loop to see if the total matches the required period. Explanation. Below are 2 short programs that show how instruction choice and addressing mode affect both readability and speed. Example 1 - copy 10 bytes from source to destination using register indirect. LXIH, 2000 L points to source address. LXID, 3000 HDE will point to destination. Use D as high, E as low. MVIB, 0 HB equals 10 bytes to copy. Copy : MOV MA equals *HL source byte. STA XD store A to *DE destination byte. INXHHL equals HL plus 1. INXDDE equals DE plus 1. DCRB equals B minus 1. JNZ copy, repeat until B reaches 0. HLT, here M memory pointed by HL, and STA XD store via DE, use register indirect mode, letting a tiny loop handle many bytes with only 5 to 6 T-states per iteration. Example 2 - add 2 constants and test the result using immediate mode. MVI, 05HA equals 5. A DI07HA equals A plus 7. Result equals 12 0CH. CPI0CH, compare A with 12. JZ label underscore OK if equal, jump to label underscore OK. JMP label underscore ERR otherwise error. Label underscore OK : success path ... Label underscore ERR : failure path ... The immediate constants 05H, 07H, 0CH are encoded right after the opcodes, making the code compact. Each immediate instruction costs 7 T-states. The CPI instruction sets the 0 flag, which the subsequent JZ uses to decide the flow, demonstrating how flags and conditional branches work together. Explanation: when a 8085 talks to the outside world keyboards, displays sensors, it uses I/O instructions that treat the external ports as special memory locations. There are 2 main ways to address them. 1. Port mapped I/O. The IN and OUT instructions use an 8-bit port address that follows the opcode. For example, OUT0x01 sends the content of the accumulator to device number 1. Think of it like ringing a specific doorbell. The number tells the processor which house device to talk to. 2. Memory mapped I/O. A peripheral is placed at a specific RAM address, for example 80000. The CPU accesses it with normal LD/STA instructions. This is like storing a toy inside a regular cupboard. You fetch it the same way as any other item. Choosing between them depends on speed and hardware simplicity. IN/OUT take 10 T states, while a memory-mapped red LDA may need 13 T states, but the latter can share the same address decoding circuitry as RAM, reducing external hardware. Practical tip: for a small microcontroller project with only a few LEDs and switches, port-mapped I/O is easiest. Each LED gets its own port number, and you write with OUT for larger systems where you need block transfers, for example reading a whole screen buffer. Memory-mapped I/O lets you use MOV or LDI loops that move many bytes quickly. In both cases, remember to set the interrupt enable EI or disable DI flags appropriately if you rely on hardware to interrupt the CPU. And always check the carry flag after IN/OUT when using the INR/DCR patterns that emulate bitwise I/O.